delete. Yeah. So if let's say somebody asks me to delete an existing node, so let's say I have something like 25, 16, 40. So first of all, is this a BST? I've just created in Rush, so you guys tell me, is this a BST? No, this is not a BST, because these nodes, let me make it 30 and let me make it 37. Is this a BST now? Yeah, this is a BST now. So now somebody will tell me that, hey, I'll give you a node and you're simply supposed to delete that node. Okay, so how do I delete the node? Let's talk about them case by case. Okay, so any node that you have been given to delete, can you tell me for which kind of nodes it will be extremely easy for you to delete them? Can you tell me that? Leaf. Yeah, leaf will be extremely easy to delete. If you have to delete a leaf, what will you do? Tell me. If you have to delete this node, what would you want to do? You would simply want to make this null. So if you have to delete it, so if you see that your node is leaf, simply make your node equals to null. This is as good as deleting it. And you can easily check whether a node is leaf or not. Okay, can you think of another case, another category of node which is not a leaf but can be a bit more tricky than this? Okay, let me think and then try to understand. Let's say you want to delete this 30. Okay, so this 30 has only one child, either right child or left child. So let's say it has a right child. So can't I say that, hey, it is as good as just removing this node and making this entire thing come over here? I mean, it is as good as making this 37 as the left child of 37, as the left child of 40. So if there is just one child, then my job is very easy. So what do? Even if it was a left child, if let's say it just had a left child, so it had something like this, 29, 27. So even in this case, my job is very easy. What I have to do is, I simply have to remove this thing and make this thing as its left child. So things are very easy, okay, where my node has just one child, So the point being that if my node has just one child, remove the node and instead of that node, bring the root of that child. Okay, one thing to be kept in mind is, whenever you are trying to delete something, then you should have access to its parent. You must have access to its parent. And can you write a code to get that done? You can simply traverse the tree, and while traversing the tree to search a node, you can track the parent through previous pointer or something else. So the way you are searching or inserting and tracking parent, you can track this. So the point is that if you know the parent, then only you can kick this out and you can position this thing over here. Okay, now let's take the tricky case where the node to be deleted has the left subtree as well as right subtree. Okay, so let's say you have something like this, 25, 15, and then had a 14. So this is what you had. Okay, let's say somebody wanted me to delete 15. I want to delete this 15. Can somebody think of how will the tree look like when this 15 is deleted? Just do some work on your pen and paper and think, if I were to delete this 15, what would the structure of tree be? Or maybe in other words, try to tell me which node would you want to bring in place of 15. See, after deletion, your tree should still be a BST, right? That is the most important thing. So you can't just bring in any random node over here. Here, whatever I was doing, that was ensuring that the resultant tree is also a BST, because if there was a tree, okay, that had just a left child, so this left child is smaller than that tree and that node was also smaller than this tree. So if you make this as the left child of its parent, all of these would still be smaller than this. So it made sense. So I have to make that sense here also. So let's think of it in this way. If I remove this 15, I want such a node to come over here. I want such a node n to come over here, such that everything in the left is smaller and everything in the right is greater. Largest from the left subtree or lowest from the right subtree? Good. So somebody is giving two options. First option is to bring in over here largest from left subtree. Second option is to bring in smallest from right subtree. Does it make sense? So what is the largest from the left subtree? Can you tell me what is the largest node in left subtree? That is 14, right? And this is 14. So what you can do is, if you bring this 14 over here, then what will happen? That since this is largest, so all of these will be smaller than 14. And since this was in the left of this, so they will continue to be greater than this 14. So this way you can get your job done. Another way could have been, so let me just do that. So there it would have looked something like this. You would have seen 14 coming in over here. Okay. Another option would have been, let's say you had a 15 and 14 over here. You could have picked smallest from the right subtree. So what is the smallest in the right subtree? That is the 16. Okay. So if you bring the 16 in over here, okay, all of them will continue to be greater because this was the smallest in this part. And since this was in this part, they all were already smaller, so they will continue to also be smaller. So what you can do is, whenever you are trying to delete a node that has both the left and right children, you have got two options. In the left subtree, find the highest value. Either you can pick that and attach it over here and your job gets done, or in the right subtree, you find the smallest value. You can pick that and attach it over here, and that's how your job gets done. Few things that you have to take special care of is, sometimes it can happen that there is a subtree of this also. So let's say you had a 16.5 and 16.6 and so on. Isn't it, guys? Yes, no? Let's say you are finding the largest from the right subtree. So in that case, you would definitely want that after deletion of this 15, this 16 comes over here, but at the cost of bringing this 16 over here, you have to modify this subtree also. But don't you believe this modification will be really simple? It will be very simple. Why? Because whatever node you are deleting, that would be such a kind of node which would either be null like it was in the previous example, or it will exactly have one child. And if it comes in either of those two categories, then we know how to handle it. So in such a kind of case, what will you do? That let's say this is your right subtree and you figured out the smallest one over here, and if it has a right subtree, then it is your due responsibility to bring this entire thing over here. Okay, and you can do that very easily. 16.5, 16.6, and then you can bring that 16 in over here. Okay, to do this you need access to this, which you know how to gain. And then the same thing is true for this. If let's say you had something smaller than 14, 13.5 and 13.4. So again, let's say you wanted to pick the greatest one from here. So you would want to bring this over here and you would want to attach this as the right child of this 13. So this way also you could have got your job done. Okay, can it ever happen that the largest in the left subtree has both the left and right children? Can it ever happen? It can never happen, because if it had, then it would not have been the largest. Why? Because, can you tell me which will be the largest node in any BST? Which will be the largest node in a given BST? If I have given you this, can I say the largest node will be the one which is along this line, the cornermost node along this line? And similarly, the smallest would be along this line. Okay, so for the largest, left subtree can exist, but right subtree will not exist. Similarly, for the smallest, right subtree can exist, but the left subtree will surely not exist. So when you implement it, then you have to do what? You have to take care of these cases. So whatever node is to be deleted, first search that node, also search its parent, then first check whether it is a leaf or not. If it is a leaf, simply make it null and exit. Okay. If it is some other node which just has left or right child, then you know what to do. Then you have to whatever is the root of the subtree, okay, that has to be put over here, and then you can make this null later. Okay, but if the case is like this, then you have two options. the largest of left subtree, which is this, or smallest of right subtree, which is this. And again, when you do that, it can happen that they have some more descendants. So you have to attach those descendants here. That will be an easy case because it will never have that they have both the left descendants and right descendants. So when you code it, there will be some edge cases, there will be some corner cases. You have to be patient, and then when you try to code, eventually you will get it accepted. So can somebody tell me what will be the time complexity of this? You are doing it in a BST, okay? So don't forget that. What will be the time complexity? Order of height, correct? Because you can locate the node which is supposed to be deleted in order of h time. And in that process, you can locate the parent also. And once you have done that, if it is leaf, order 1. If it is, even if it is a node that just has one branch coming out of it, then also order 1. And even if it has, let's say, 2 branches coming out, then how much time will you take to find the maximum and minimum? You just take order h time, right? Because you continue moving in one direction only. So overall, it will just be order of h. So deletion, although it has some more cases, but effectively it is order h only. So you have to be very good with these operations.